all the potential people, so you'll all get it. But let's see, if I go to courses and I go to here, and did I put the little email thing in there? I did not put the email thing in there. How do I do that? Oh yeah, I'll do this. Add in tool link, email. There you go, boom. And I'll call it email, because that's a good name for it. Email. And so then I can just send boom. For you, FYI, you can log in remotely via the BD Collaborate recitationists. Maybe, perhaps. This is the noise. This is the face I make when I come up with stupid shit. Okay, that's where I look at. I'll just write the same thing here. Should be something in the body, right? For the exam review session. So, FYI, comma. And then, always got to end with something. So I picked regards. It sounds kind of weird. I don't know. What I say is sincerely, best wishes. I have one colleague that went cheers all the time, but he's British, so he can get away with that. In my opinion. So we can like collapse this thing, right? Okay. So let's talk about exam 1. Woohoo! We purposely made exam 1 about only 5 classes. Try to get our feet into the water, dip our toes into the water, get used to the difficulty of dynamics, learn from it. So we are covering this stuff of chapter 11, only 5 classes worth of things, where particle kinematics is the big topic, and here are the potential topics that we would cover. Very much like if you want to go and look over the homework. You can see in the first class we covered fundamental kinematics. We're using those fundamental equations, simple equations, but we note that we can make complex problems out of those. Projectile motion, I always think of that as being the first dynamics problem, right? Early man wanted to get food. He has rock. He throw rock at food. Projectile motion problem, right? Kinematics. Constant acceleration problems, relative motion. We can deal with little vectors, little vector triangles and stuff like that. Constrained dependent motion, which I usually associate with pulley problems. Rectangular coordinates, doing just problems with that. A lot of times that's constant acceleration problems, but they don't have to be. But we're dealing with 2D things. Coordinate transformation, because we want to use path coordinates or polar coordinates, and we need some tool to be able to go between them. So this is the equation sheet. There's the section onto the on there. You should have access to the equation sheet. Probably print it out and practice problems while using it, because that's your lifeline. And you know what's on there and what is not on there as well. So I have a bunch of problems we can go through, but I'm taking requests, so it's up to you. What would you like to go on? You can pick a problem. Here's problems. These were old problems from the Coast Guard Academy when I taught there, and I decided, hey, I'll just give them away. You guys can pick and you can use these as practice. But I can also pick things out of the book. I can do homework problems that we've already had. In my class, I've been pushing something I call suggested problems in addition to homework. That's not a really snazzy title. I think I could pick a quick, that's a lot of words. But I'm just saying these are extra homework problems, like, hey, if I were going to pick some out of the book, here's some more that I would do, right? So we could do any of those, or we could invent a problem, or we just stare at each other for a while, whatever you want to do. I'm down with it. What do you want to do? Anybody? Be bold. By the way, there's a sign-up sheet somewhere. It should be circulating around. Sometimes you go someplace to die. If it did, you could blame him because it's sitting right there. Don't let the sign-up sheet get stalled with you, right?
Homework 3, problem 3.
Okay, homework 3, problem 3. All right, let's take a look and see what it is. Boom, boom. I better be able to do it. Let's see. Go to dynamics and assignments. Homework 3, problem 3. Boom. Okay, yeah. So actually, the one that was actually on that that sheet. I think it's this one right here. All right. So let's see. Is it the identical problem, or did I? Yeah. Actually, it might be the identical problem right there. Looks like everything is the same. All right. So in a problem like this, and in many dynamics problems, now we can't quite do the same thing on an exam as we do in homework. There's only, because we're timed, right? We have a small amount of time. But with many dynamics problems, you're not going to know exactly how to do it when you first look at it. So you have to read it and start looking for hints of some place to start. And I think a lot of solving dynamics problems is like going in a maze where you have to kind of go down and you might run into a blind alley, right? Turn around, have to go back. Sometimes that's how you have to solve things. Hopefully not. Hopefully you'll start to move and you start to go a certain distance through the problem and you'll suddenly go, oh, I got it. But it's very rare that you would just look at a problem, stare at it, and for that to happen. So you got to get moving. I can't emphasize this enough. People run out of time on exams, and a lot of that time is spent just staring at the paper, thinking. I don't know for sure, but I'm pretty sure that's kind of a useless wasted time. It doesn't, I don't know if it maybe that happens. Maybe people get an epiphany after they stared at something. But those epiphanies, that aha, usually takes place while you're writing stuff down. So just start attacking this problem. So for instance, aside from just, by the way, what I'm trying to do is help you prepare for an exam, not just because of this problem, but the thought process that you need to be going through in order to tackling the problem. So you read it carefully. That's one of the hardest parts, is right, reading the thing, looking at the picture, trying to organize your brain so that you could have that aha moment. Okay, so we see a train that's right here at point A, and it's 1.6 kilometers away from that intersection. And it's traveling at 130 kilometers per hour when it applies its brakes. So it's slowing down, and it slows down at a constant rate. All right? So you can just picture this train as he's moving down. We get a snapshot right here, and he starts to move. All right, by the way, I think, okay, so now I need to, actually this is not identical to the homework problem, because I think I changed the homework problem from, this is like the original source. I said there was another point where he got to, and we were able to measure his speed at that point. So let me switch back over to right here to actually get the correct problem.
Yeah, that was, and then the only thing I think that you changed is that that there's a point B and the car is at point C, but that 96 kilometers per hour was still in that problem.
Yes. And so, but what I just want to go back to there because I wanted specifically to try to go through the thought process, right? So we see, we have that information right here that he is traveling at a known speed here and a known speed here. And we're probably going to want to know something about this, because if we keep reading down below, we find out this maniac right here is going 80 kilometers per hour, but he sees the train and he's going to try to beat the train. Very bad idea. Do not attempt. But anyway, so we have to try to figure out. Lastly, we find the happy ending to the story. Although he's just gonna, we know bad things are going to happen to this guy later on in life. It's just going to catch up with him. This type of reckless attitude. But he beats it by 4 seconds, right? So we start trying to think our way through. It's like, okay, how am I going to approach this? Well, first off, maybe I want to know what the train's deceleration is. So, all right, I recognize that I'm given 2 velocities and a distance, so that I recognize I want to use this right here, this fundamental kinematic equation, not fundamental kinematic equation, I should say, not G, silly, acceleration, and then delta, I'll call it X. I just didn't have a name for it. And that's the train, right? So we can say here's the velocity of the train, and here's the initial velocity of the train. So we can get the acceleration of the train. And they put everything into kilometers per hour, which is kind of a pain. So let's convert all those. And I might even want to go like this. This is right here. I don't know. I guess I'll call it a B. Not doing a great job with the labeling of things in a consistent manner, but it'll work. So anyway, what do we take? We have 130. You got to help me out with math here, because I'm terrible at math. Right, so we want to divide by 3,600 seconds per hour, right? But we need to multiply this by 1,000 meters per kilometer. And I didn't leave myself enough room. That was great. There you go. Ooh, that's not an eraser. Here's an eraser. So, what does that turn out to be? 130. We can even just see what the posted solution is, right?
36.11 meters per second.
Thank you. And doing the same thing here with the initial, well,
Wait, that was.
I think that was the initial velocity, wasn't it? Yeah. I'm sorry. Thank you. And this is at B. It's given it a name. 96, right? Which is the same thing as 96,000 divided by 3,600. So we get 26, right?
26.67.
Meters per second. So let's put this in here. So it's going to be, here's our 26.67 squared equals 36.11 squared plus 2. And this is the acceleration of A. And the distance between these two things is 0.8 kilometers, right? Or 800 meters. So this should be a negative number. So you can square that, and then square the 36. Subtract out, divide by 2, divide by 800. Am I correct that I get a negative 0.37? Doesn't sound like familiar, but maybe it is. Meters per second squared. Let's just double check our numbers as we go through, just for the sake of this is solutions. Not now, Adobe Acrobat. You always want stuff. It's very needy. There you go. We converted it, and sure, we got the right answer. Oh, okay. So we got to right there, and now it would be good is to figure out how much time it takes to get to O. Right? How would I go about trying to figure out how much time it takes to get to O? Double check, that's the last next thing I did. Yes. So, because I already have the deceleration, I can use my position right here. This equation right here of initial velocity times time plus 1/2 acceleration times time squared. I know these positions, right? If I could say, and by the way, I could use either the one at A or at B, but it's better to use it at A because this car is at that location at the same time, right? So I get to here and I say that this is going to be 1.6. No. Yeah, okay, well, we'll say that we'll say that 0 starts right there. Okay, yeah, so 1,600 meters is equal to 0 plus initial velocity of 36.11 times time plus 1/2 negative 0.3706 t squared.
I thought that the rounded answer should be, the acceleration should be 0.3705.
I got 0.37056 with mine. It probably, you might have rounded something off on the
Yeah.
beginning. I left it in my calculator, so I'm pretty sure it got to. But we're talking about, yeah, it's just only we don't have fewer decimal places than this, we're gonna be okay. The 4 sig figs is fine for most stuff. But anyway, so we're gonna come up with something that's t squared plus something t plus something equals 0. And so that's going to be 2, so negative 0.185, call it 3. And this guy is still 36.11. And this is going to be a negative 1,600. So we can solve for t by going negative b plus or minus the square root of b squared plus 4ac over 2a. How many people actually still use this?
The quadratic formula?
Yeah. You just use your calculator.
Yeah.
Just get the root.
But
There's
I-
some benefit to doing this. by the
Yeah,
way.
I would just
Then you could recognize while something's going messed up, you could kind of diagnose going backwards. But why
Most
you end up
recent time
getting
I used-
imaginary numbers?
The most recent time I used it was in differential equations, just because.
But doing like things like control circuits and that type of thing, you could the imaginary numbers mean something. They're not just imaginary. I don't like them though. I don't like them. That's all right. But anyway, if you solve for this, I'm not going to bother, and you get 2 different times, and one of them is negative, and that's meaningless. So actually, one of them is really big. So I think it's 68.09 and 126.9. And my small brain just forgot what that was. Was it 68.1, did I say?
68.09.
And then we had one other number. But this is the one that we care about because it's going to happen first. We could use that logic right in there. And it says that the car beats it by 4 seconds. So the car is at the intersection 4 seconds sooner. So the car's time, so this is remember, that's the train arriving at the thing. But now for the car, we can find its time is going to be 64.09 seconds. And now we can find its acceleration. So we take the car's acceleration, and because we have the distance c, which is 2 kilometers. Wow, he's even further away. I guess it looks that way. Okay. So we could take that x for the car. Yeah, we had to do it by position. Okay. X naught plus v naught time plus 1/2 acceleration t squared, and we know that he's going to go 2,000 meters. His initial, we never did this, VB, he was what, 8, how fast was he going? He's just going 80. So 80,000 divided by 3,600, so 22.22222. So 22.22 and 68.09 plus 1/2 acceleration of B, 68.0.
It would be 64.09.
You're right. I just glanced over there. Thank you so much. Yeah, I just looked up there. So I guess you do the number, right? 2000. Flip it down. Flip it. It goes 64.09 times. You know, we're gonna subtract that, multiply it by 2, and then divide it by 64.09 squared. Boom. So is he? Let's see if I get this right. 0.280, call it 4 meters per second squared. How'd we do? Okay. And now we need to know. Okay, so going back to the way that the problem is phrased, right? We've got to keep, we got sort of, we have a lot of information here, but we need to now find the determined part of the thing. And the relative velocity in kilometers per hour, so it's kind of better that we did all this, but then we'll convert it back. The train with respect to the car when the car is in the intersection. So we need to know two things. We need to know how fast the car is moving when it's in the intersection. We know its acceleration, we know its time, so we'll be able to go and figure out what its velocity, or we will find its velocity, the speed first, when it's in the intersection. And then we also need to figure out where the train is, right? And the train's velocity at that time, right? So a couple more things to find out, but not much more. Like I said, this is a long problem, but it has the quality in it that's making your brain kind of try to think through something that's complex. Not crazy complex, but not immediately obvious, right? And that's the skill set that dynamics kind of forces you to get to build, that muscle of figuring your way out around stuff. Okay, so we need the car at that time. So the velocity of B starts B.
VC, I think cars.
The car is the C, isn't he? Thank you. C is going to be equal to its initial one, and that's going to be, well, that doesn't make a lot of sense. Okay, I'm just going to call it this way. Just forget about the subscript there. Plus this should have been C all along, right? And we have the time. We have the time when that happens, right? So we can figure out that he's going to go 2, 2, 2, 2. And that its acceleration is 0.2804. And its time was the 64.09. So 2.22. And 0.2804 and 64.09 times plus. All right, so you should be going a crazy 40.19 meters per second, which we could now multiply by 3,600. Actually, I just multiply by 3.6, couldn't I? Because I'm about to divide it by 1,000. So 144.7 kilometers per hour. And then we can figure out what the velocity of the train is going to be. Maybe let's, I don't know how to write this thing. I'm going to go at t equals 64.09 seconds. All right, so same thing here. We're going to take its initial velocity, which was 36.11, right? Plus its acceleration, which we found to be somewhere, was negative or something, right? Yeah. Did I erase it?
Yes, you did.
What was the answer? What was there? 0.2 something?
3706.
0.37?
06, yeah.
Thank you. 64.09. And what did I just do? Yeah, it just accidentally hits hit a button. So I'm going to say that I don't know, okay, I guess 12.36 meters per second, which is the same thing as 3.6 times that. 44.45 kilometers per hour. Now we're asking for the relative velocity of these things, right? So that made that a pain in the tuck because I have so many things. So break it down into components, into rectangular components, because that was part of what this problem was about, right? We were trying to combine like 3 things into one lesson. We were trying to combine rectangular coordinates, constant acceleration problem, and relative motion. And dependent motion, that's a lot. We used to do this whole section in 4 classes. Actually, when I first came here, we did it in 3 classes. We did all particle kinematics in 3 we kept extending it. Maybe we should extend it to a 6th class. I don't know. I'll talk with Dr. Rico and Dr. Orlo. But anyway, so we have the velocity of c. Well, that was not too bad, right? Because no, that's actually the one we have to do something with. So we take a 140. I got to double check that I got that answer right. 144 times. Let's see. Yeah, we could do the cosine of the angle. Is that correct? Sure. We're at 60 degrees. Yes. I plus 144.7 sine of 60. Let's just do a double check, and this is kilometers per hour. Hmm. 144. Yeah, okay. All right, so yeah, we what is that right there? Why do I have 144.7 degrees?
I think you mistyped it.
I think so too. I think there's, once again, I write these things out. I don't know what I'm doing while there. Maybe I'm like watching some Buffalo Bills games or something. I don't know. I keep finding mistakes, but yeah, what are you gonna do? You get angry at me for making mistakes?
Yeah.
I'm sorry. But I try so hard. 144 point. I used to have a calculator that would do this for me. I don't know what happened to him. So 72.35 I and 144.7 sine of 60 and 1253 J. And then we know that, what do we call him? A? I don't know. Doesn't make sense because A is a location. It should be like T. Should have called him like T for the velocity of the train instead of A, because A is actually a location for them. Anyway, this one at that instant was 44.45 I kilometers per hour. And we want to, we always had to read this right here. We want the train with respect to the car. So that's going to be the velocity of A with respect to C. So we take velocity of A, whoop, that doesn't even look like a V. Velocity of V, velocity A, minus velocity C. So 72.35 minus 40, whoop, other way around, boom. 44.45 minus 72.35. And we can just leave that as parentheses. 125.3 J. kilometers per hour. So it's going to be negative in the x direction. That's cool.
Then it would be negative in the y direction.
Yeah, it would be negative, right? Right.
Because it would be 0.
Yes, because the train doesn't have anything in the y direction, right? So thank you. So we'll take a 44.45 and subtract it. So you get a negative 27.9 I plus a negative 125.3 J kilometers per hour. Cool. But now we want to do, this doesn't tell us nearly as much as finding the magnitude and the direction. So that relative acceleration right there, first off, it's going to be in the third quadrant, right? Both negative, negative. So we find VA with respect to C as the square root of negative 27.9. I can't even read my own handwriting. Was that a 6? It was a 0. Squared plus negative 125.3 squared. And squared plus square root 128.4. And the angle here, here you go, I'll just call it a theta, but just to give it a name. Should probably figure out a way to write that out. Okay, so I don't bother with the signs and when doing the angles right there. I know what quadrant already, so I'm just going to go rise over run 125.3 over 27.90 and 125.3, 27 point. By the way, always check that you're not in radians. It's a good idea. We'll miss you. I always am finding myself forgetting that I'm in radians when I'm in radians. So anyway, writing this out as an answer, we should give it a 128. You could give it 4 sig figs. In fact, the technical answer rules for sig figs in engineering mechanics, as written by Beard Johnston in their statics in the first chapter 1, is always use answer with 3 sig figs unless 1 is the first digit, and then answer with 4 sig figs. Honestly, it's in the book. It's that right there. And I know Dave Mazurk, one of the authors from there, a name dropping, plop. He teaches the Coast Guard Academy. He's in the office right next to me. Really brilliant guy. Handwriting so good it could be a font. That's how good. So anyway, I'll put in that extra sig fig there. Kilometers per hour. He's also a Buffalo Bills fan, so there he's got that going for him. And I am too, so don't say it. Don't say it. I don't want to hear Jets fans tell me. We're still in the grieving stages here, so you gotta be kind to me. All right, so I'm not gonna do the part B onto this. I don't think we don't want to spend any more time. We spend a lot of time on this, obviously, but I do want to look at the triangle. Get a lot out of the triangles. There's a lot to be learned from those triangles. And if you had a ruler that had nice increments of scale on it, you could scale this thing out and do your best with trying to figure out what the angles are onto the thing. But we have a car that's traveling up here. By the way, I always have to rewrite this equation out, right? So I need to write out VA is equal to VC plus VC with respect to A. I want to write out that equation right there because I remember how to add triangles together. I don't remember how to subtract triangles, right? So I'm going to take that, this is VC right here, and I'm going to add this to it, and it's going to result in VA. And let's see, so this right here is VC. and my VA is definitely going this way right here, but it's smaller, so it's going to be something like that right there. So, in order to have these two, all right, so it's got to be like that right there. So I didn't do a great job of my values. Let's see. If I had scaled it, was just a little bit careful. That looks like about 60 degrees maybe. But that's got to be like 77. Although it's still something along those lines right there. Right? Because that nose goes to the tail because we're adding these two things together. This V, C with respect to A. And you were like, why are we bothering with this? Because I think that there's a difference between being a student and being an engineer. And what's the point in doing any of this stuff if we can't visualize it? If we can't like pick it apart and understand what's actually taking place. So I think a vector triangle is so much more wisdom going in there than just the numbers by themselves. So much understanding taking place. And especially if you start to apply it to like, okay, who cares about this? But what about if we're talking about like your Maverick and Top Gun, you know, and you're trying to figure out where the approach vector that you need to be able to, you know, with the missile that's coming in towards the thing, you know what I'm talking about. Yeah. Put some life and limb on there instead of just this idiot that's trying to outrun a train. It's a cautionary tale, not a challenge.
I'm just a little confused as to why the vector C with respect to A is pointing to the left downward.
Okay, so first off, mathematically, we have it right. So we're feeling okay about that. But now we're just saying, okay, so it is sort of a weird thing, right? It's like C with respect to A. I might have screwed the thing up. So let me double check that I got it right. All right, so I want to find. Yeah, you're right. That is screwy. I gotta get my head turned around. But that's good. Did I get the right answer, by the way? I don't know if I got the right answer. This could be the right answer, or if I made the same mistakes over again. No, that should be A with respect to C. Yeah, I wrote that wrong. Sorry. This would be wrong. Yeah, thank you. I wasn't thinking. A with respect to C, I'm still doing it wrong. A with respect to C. Now that makes sense. That A with respect to C. It's like, what does A look like to C? Right? As C being the reference, we're like, okay, what does it look like? Well, A looks like, first off, A looks like if you are C you're not like, maybe you're forgetting about the landscape and you're just focused on that particle. What does that particle look like it's doing to you? It looks like it's coming right at you, right, for one thing. So it's coming that direction with respect to C. It also seems to be moving over that way right here because you're going so fast over to the right. All right, so he's going quicker over to the right. So it kind of looks like it's wherever its position is, that's not related to this, but it's what its motion appears to be doing to C. Does that make sense?
Yeah, that is.
Okay, better sense. But I'm sorry I mislabeled that.
No, that's all good. I just was.
It's tough to do this little juggling act here up in front, like a monkey on a stick, right? But I'll still be that monkey for you. What problem would we like to do next there? Having given 39 minutes to this one.
So the problem's going to be like 45 minutes on the exam, like per problem?
Okay, so for my class, I generally try to cover as many topics as I can with as few problems as I can, and I try to time it so that I can do it in 1/2 the time that's allotted, right? But then I also try to err on the side of more time. So sometimes I aim for that 2.5, but I can't quite get all the stuff I want in there. So I have found that I can't really ask more than 3 problems. Sometimes I could ask 4 problems if they're straightforward enough. But it isn't that I'm trying to see how much torture I can impart upon you. That's just one of the side benefits of the job. No, I'm not, I'm trying to measure your mastery, and your progress, right? So I think it's true. I have, we share exams together, Dr. Rico and Dr. Olep and I. We work really closely together, and usually send each other the exams. And so in the past, I've seen that they're about the same, about 3 to 4 problems. And like I said, so in that spirit, because you have 75 minutes, so each problem should be no longer than 25 minutes each, assuming that they're equally difficult. Usually I'll go a 30-30-40 time split, and that's because when I time them, I take the problems myself, I see which ones took the longer, I'll give that one more points worth of time. Is that too much information? Okay. The Coast Guard Academy problems right here. So I taught that with also a group of awesome professors that we work. Our offices right next to each other, and we would each pick up a topic or a group of topics and write the problems, and we'd all write them together, and then time them and critique them. And so that's the product right here. I don't think I wrote this because I would never have used that font. Right, so that's but I would have written an Angry Birds problem. I think I might have suggested. I think this is
the answer above the problem.
Yes, the answer is above the problem. So that actually have had a few students that go, why don't you just use the 25.2? And I'm like, oh, that's actually the answer. Because I figured I'd tell you the answer. So you had something to aim for, but that was spring of 2016. I know I did this one because I'm big time Michael Jordan. Oof. Is today? I think, yeah, today. Today's Michael Jordan Day. It's 2, 3, 23. So his number was 23. Actually, for a little while, it was 45. But 20, you don't even know who Michael Jordan is?
Let's go play.
I was going to I'm not going to do this. I'm not going to have you raise your hand if you don't know who Michael Jordan is. Because I'm just gonna crawl up in a little ball and just in sadness of how old and it's not your fault, it's me. It's not you, it's me. Time, not our friend. But here's like 3 projectile motion problems, fundamental kinematics problem. But these were actually for classes that were 50 minutes long. I'm not trying to, and generally speaking, there might have been 4 of these problems. So some of these are a little bit shorter than you might expect. So I'm just trying to give you an expectation. That's my recollection. But also some of my fellow professors were merciless. Merciless. This is a problem I wrote. I know I wrote this problem. So here we got I think it's a polar coordinates problem. I don't know.
It says fundamental kinematics and polar coordinates.
Yeah. So that's, I think we can trust that because I wrote it. But sometimes I mislabel things. I think I've had a couple in the packet of old exam problems that were all messed up. But let's read this. I think I did provide this graph with the thing. And there's a trick. This graph is, okay, so, I use the magic word, I gotta be careful. I'm never trying to trick students, but I am trying to sometimes just measure by way of a problem that's actually wicked easier than someone might think to have to do. And so that's the nature of the part C in this. But then I'd feel bad if someone spent like a really long time trying to do the thing. You'll see in a second. So the fundamental kinematics, so a path, so this is where the problem actually starts. The path of a particle shown in the graph is represented by r is equal to 1.5 plus cosine of pi over 2t. By the way, anytime you see that pi stuff, remember you got to put your calculator in radians and turn it back later. Pitfall. You also see that theta, which is going to be measured in radians, almost for sure, is pi over 2t squared. And we want to use that, we said find So we would have defined the velocity at t equals 0.5 seconds. Find the acceleration vector. It didn't say, oh no, it says using polar coordinates. Okay, cool. So we didn't have to do a coordinate transformation. See, I didn't actually, at the Coast Guard Academy when I was there, that's not in this book. So I didn't actually do the coordinate transformation, but I would tell you now I would ask you to find the, I would ask you as part of that because it's a really important skill set. And that would make the problem a little bit longer. And that would probably be a problem in terms of length that I would ask. I might also, let's see, do a sketch that right there onto the thing. All right, so this is fairly straightforward here because these are functions of time. All right, so the big thing to do when you have a polar problem, you want to have the variables of interest. I go the VOIs. I like when something when one of the words is of. I like to make it lowercase. It just amuses myself. I just amuse me so much. So what we mean by that is that we find R dot, R double dot, theta dot, and theta double dot. And we look for the equations that we're going to use here. In polar coordinates, we have R dot is the component multiplied by the radial unit vector. R times theta dot is the E theta. These things are worth memorizing, by the way. That can save you some time. Or just being so familiar with them that you just have to briefly glance at the equation sheet, right? Because you've digested the thing so much that you don't really have it memorized, but you pretty much know what's going on. And then the acceleration is going to be R double dot minus R theta dot squared. And one way to help you remember these is remembering make an association with the physical meaning of the piece. Or if someone has drawn a cartoon for you, that kind of helps you try to remember the thing. A mnemonic, if you will. R theta double dot plus 2 R dot theta dot E theta. So we know that that's like the rod getting long, that's the length of the thing getting, and the rate of the thing getting longer. This right here is actually centrifugal acceleration, kind of hidden. It's negative because it's pointing towards the center of the polar coordinates. We see this guy right here, it's about the thing, the rate of the change of the speed of the rotation of the thing. So if you're looking at the tip, you can even think of associated with like sort of tangential type of motion acceleration. And here's our good friend Coriolis, which is just a freaking mystery. But not really. But you can see that those are all the ingredients that we need. So when we see a path, or excuse me, a polar coordinates problem, we want to search for these variables of interest, right? We want to think that's sort of like the pivot, if you will, and mentally of where we're going to try to approach the problem. So we can actually start getting some of these right away. Like we could go ahead and we could plug in 1.5 times or plus the cosine of pi over 2 times 0.5 seconds, right? And we can find a value. And we can find a value of this right here. We can go pi over 2. And in terms of the test-taking strategies, remember, partial credit's king, right? What you have written on the paper is what you get partial credit for. So write some shit on the paper, right? You gotta write the thing on the paper. It ain't on paper, you can't get graded on for blank sheet paper. So sitting there staring is not accomplishing anything. Writing down the stuff that you know can be the thing that makes you go, oh, I got it, right? So less staring at pages, more doing of things. And now, get very, I can't even remember, how do I turn this into radians? So I have a favorite calculator, but I have the app that's almost identical to my favorite calculator. And it's the word mode. There it is, mode. Radians. Boom. Okay. So 0.5 times pi and divided by 2 and take the cosine. Seems like there should be something multiplied in front of it. No, there's not. Okay. So just 1.5 plus. 1.5 plus. Okay. So someone has to please keep me honest. Or as honest as I can be. I'm pretty honest. I think I'm an honest guy. It's in meters, right? And then we get 0.5 squared times pi divided by 2. 0.3927 radians. Rads. Radical, man. All right. So we need to take, in order to find the r dot and r double dot, we need to take the derivative, right? So that's just going to be 1.5 goes away. Take the derivative of a cosine is a negative sign, right? And we have to multiply it by the thing that's in the front of it. So it's just what, pi over 2, negative pi over 2 times the sine of pi over 2 t. So stick them in there, and negative pi over 2 sine pi over 2.5. 0.5 pi times 2 divided sine was negative 0.7071 meters per second. It just occurred to me that I actually have this written down, so I could double check. Sometimes the brain just don't want to do things. Okay, so I got that one wrong. Oh, I did multiply it by pi over 2. That's why. If I multiply by pi over 2, I get 1.111. And then I can do the same thing again. Take the d of r dot dt, and still going to be negative, but it's going to be pi over 2 squared cosine of pi over 2t. Get that right? Sure. And plugging in numbers in, negative 1.745 meters per second squared. These I could probably just write right next to it. This is going to take the derivative with respect to time. This is going to be, oh, that's just going to be pi t, right? That 2 is going to come down, get rid of that 1/2 right there. So that's just going to be pi times 0.5, or 1.571 radians per second. And then it's going to be equal to pi. 3.142? Sure. Anybody one of those people that like memorizes pi to like so many digits for some stupid reason? I don't understand that, but more power to you. More pi to you. More pi for you. I love pie. I don't know. We had to go poll pie versus cake. Who's a cake person? Let's see the cake people. Cake people? How about pie people? How about people don't care? Both. People that don't. Oh, both. There you go. Oh, that's good. All right, cool.
I'm a both, but it's not like a fruit cake.
I think I'm going.
Why do you
I think I'm
pie?
going pie. I mean, if you know, you had cake and pie, and then you gotta pick one, and you can't have both. You can't have both. All right. Anyway, you know what we should do? This right here. So the velocity vector, we just take first the r dot. It's easy. No, it's not negative. It's this guy over here, right? 2.207 ER plus. We have to go r times, so it was already written over here, r times theta. No, I just did that wrong. What is wrong with me? Think. Thank you. Negative 1.111. And then now we go 2.207. And the theta dot is 1.571 E theta. So I don't know if it's the greatest idea to have this thing up here and only be using this little tiny piece of board. Doesn't make a whole lot of sense, but. And what do we have here for a value is, I didn't give this enough sig figs, but 3.47, that's all you're getting, meters per second is the answer right in here. And the acceleration, we're going to take our r double dot, a negative 1.745, minus our r of 2.207. There's our theta dot squared, 1.571 squared E theta. I know, I was in the way, sorry. And go to the R, just regular old R, 2.207 times theta double dot, which is pi, and 2 times our R dot, which is
Would
negative.
that be, for the first one, would it be, you have E theta, it should be ER, right?
Excuse me 1 second. This right here?
No, the unit, the like.
Oh yeah, you're right. Oh, thank you. Yeah. Thank you. My mind drifted. Can you imagine that? Yeah, probably could imagine. You could probably believe it. Now we have an E theta. And so we get acceleration. Should be the same thing we had before. It's negative 7. I know, I'm in the way. I'm sorry. 3.44. E theta meters per second squared. I just crossed it out. And the last part of this, as I alluded to earlier, is a trick. Well, you could, all right, so we're going to sketch the velocity vector onto this, but, and you can see I already put a little point onto there. So you could actually have plotted this out, because this is, in fact, the vector. I mean, this is the path that is described by this motion right there. You could work it out, do it in Excel. You could plot that thing out and end up like right there. But this is just a 1 second thing. When I say, let's see, it's my class. Let me see my class, the people in my class. What is, I say the word velocity. What's the next thing that comes out of your head?
Speed direction.
Something. There's a phrase. I say velocity is always
Tangential?
tangent to the path. Most important thing. All I have to do, draw a line that's tangent to the path. It's going to be up and to the left, right? Or you could even guess that, well, hey, maybe it's down and to the right. Maybe, could it be down to the right? And you start to think, well, like, okay, well, where does the thing start? So you just put in 0 right in there for its at time, and you can see it's 1.5. No, actually it's going to be 2.5, right? Because you put in 2, that's going to be 1 plus there. So you know for sure it is, in fact, starting right here. So it must be up and to the left. Does that make sense? Simple, though? That's the thing I want to extract right here. Velocity is always tangent to the path. It's a really important thing. But I also might, I would probably ask this problem and say, give me the velocity, probably, because I don't know, maybe I'll give you the acceleration in, well, that would be mean to say in path coordinates. That would be very mean to go path coordinates, but I wouldn't do that. It would take too long. But it could be asked, but give me the acceleration in rectangular coordinates. Then you have to do a coordinate transformation. Not terrible, not fun, but not terrible. But it would demonstrate that you're able to do that, which is the point of the exam, right? Just to demonstrate, hey, can you figure this out? Do you have this skill set? All right here. And then when I grade it, it's measuring, you weren't able to do this, but you demonstrated this. Okay, I think you have like maybe 75% mastery on this problem. And that's how kind of a graded thing is. Instead of going, you did this wrong, 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 you did this wrong. A lot of times that adds up to a whole lot. Like I have to go backwards and I go, nah, they didn't. They did better than that on this. So anyway, just to telegraph the way that I approach the problem, which I think is better than. All right, so other types of problems. What we'll talk about. By the way, is this being, well, no, that's not a fair question because you're going to just be kind and tell me that it is working. But I just want your feedback at some point, like how I can improve to help in these help sessions. Maybe I should not solve the problem all the way out, and just get kind of to the thing where you're going to go, oh, I got it, so we don't waste so much time putting the numbers in. I don't know. One method I had thought of, of just flipping through the book and almost, I'm thinking of them as like flashcards. They go, what kind of problem is this? How would you approach it? And then go to another problem. What kind of problem is this? How would you approach it? What do you think the trick is? Right? And just, kind of through volume, trying to like look at the thing, try to process it, try to read it carefully, see hey, what is the approach onto the thing? But I think the details are also important, like the maneuvering through the math, trying to get to the end. Most important thing is that aha moment, trying to get better at getting it. So I'm just talking because I don't like silence. So please speak up, interrupt me with a request.
Can we do a projectile motion one?
Sure, absolutely. Projectile motion problems can be surprisingly difficult. A lot of times we will see ones, okay, so these first, I think, I might be wrong, but these three are almost identical to each other. And by the way, sometimes there's a couple shortcuts you can take in a lot of the problems. I tend to not use those, but there are some shortcuts in some problems. But we have a lot of times we want, so both of these, okay, so both of these first two are both initial velocity problems, right? Trying to find what is the initial velocity to land at a particular spot. So they're kind of like identical to each other. We have this one right here where you try to figure out what the distance is going to be when this thing lands. For projectile, but I also have a bunch of other ones. So I put them in here because I'm like, I really want people to, not just memorize a particular kind of problem, but be able to like think your way through the thing. And some of them I would never ask on an exam because they're too hard to do. Just let you know, just would never do it. But you take a look at this kind of problem, and so let's, while you're talking, let's do the same thing I just suggested we do. Let's look at these problems. Each of them, there are a bunch of projectile motion problems in a row, and say, how would you go about doing this? Right? And I'll answer the question, but first, I want you to think. I want you to think about it because me just telling you things isn't as helpful as you trying to think, right? And then being told what, or confirming that you got it right. But you take a look, and you go, okay, it's observed that the skier leaves the ramp A at an angle of 25 degrees with the horizontal. If he strikes the ground at B, which is 100 meters right here, but down the length right there, determine his initial velocity, VA, and the speed at which he strikes the ground. So I had both of those things. Well, it's similar to those other problems, but there's a little bit of a complication in there that you might need to write sort of one approach is you could write like an equation for that line of slope right there. No, you don't have to, because he does, yes, no, you can find the coordinates. And you just have to decide where 0 is going to be. Like, a lot of times we'll make that 0. It's a good spot for 0 to be. But notice you're going to have a negative y, right? You need to include that, but then also take, with this 3, 4, 5 triangle right here, you could probably just do this, do the coordinates kind of in your head, right? Because you go 4, so that's 5, right? So that's like 80, right? It'd be 80 this way right here, and it'd be 60, but then another 4, so 64, negative 64 right there. So you pick out the coordinates, and then you can put in the two equations that we have together that are really, for most projectile motion problems, defining what's taking place. Not always, but for the most part, what we do is we say in the x direction, it's a constant velocity problem. In the y direction, it's a constant acceleration problem, where gravity is the acceleration. And the two things that link those equations together are time. So we write out x is equal to x naught plus Vx. And of course, that velocity is constant. And then we have y is equal to y naught Vy t plus, well, I go negative, right? Negative 1/2 g t squared. We also know that we have Vx is V0 times cosine of initial angle, Vy, thank you, VO, I hope so. And we can plug these in, solve for t, replace this t and that t with this one up here, and now we have an equation where we have unknown velocity, and we have a position, right? So we can put in the final position x and y in there and solve for it. And another approach to this, though, just for your information, is to find the time when they land, right? And then go back and then put that time back into one of those equations, and you'll be able to find what the initial velocity needs to be. No, did I say that wrong? No, I think I'm incorrect right there. Sorry. Yeah, I think I'm incorrect. I don't know. There's a way that you can cheat in this. Yeah, that's not the case. All right, so sorry about that. Is this the one where they do that? The time, plug the time back in. No, we're okay. No, they don't. But anyway, we could find even without knowing the time when we have it back over here. As soon as we have the initial velocity, we can find. So that's VA, right? We could find that. That's what I'm calling this VO right here, going through that process. But if you want to find this one right here, to find that latter part of the thing in the y direction, we use this other equation. We can say the velocity in y squared is going to be equal to the velocity y initial squared minus 2g, and then go delta y, right? So now you can find the y component when it hits B, because we'll have the vertical distance, right? And then you define the speed, right? They want to know the speed when it strikes the ground. Remember that this one is always the same, right? From the beginning. So just had to make sure you don't just gloss over that if you were to do that problem like this. But this is very similar to those other problems. No, you need to have the distance. Here is a problem where you need to, a variety of the problem, where now you would need to sort of have an equation that relates where that position is going to be to the slope with that 10 degrees right in there. It's really not that difficult to do when you have the initial velocity. So basically, the way to approach this is to figure out, because you have Vx there and Vy there, because we've broken it down. We could break that down because you have the angle and the, oh, well, that's a little bit of a cheater too, because that angle, you got to be careful, that angle is actually 55 from horizontal. That's a dirty trick. Easy to overlook that, just go with the 45. But anyway, the only one we really care about is the y, correct? Because you can figure out like where that thing is going to drop down. Let me take that back. Yeah, you can find the time when it's going to land. Yeah, okay. Mean. It was mean. What you say is you go d time. So x position is going to be d times the x of x. What am I doing? Cosine of the 10 degrees, and then the y is going to be d times the sine of 10 degrees. So you can relate that the position x is equal to well, let's treat it as 0, but you go Vxo times time. So it's obviously going to equal to d times the cosine of 10. So you can stick in that t is equal to that right there, right? We have d times the cosine of 10 over the Vx0. And then we also have y is equal to y0, right? Just treat him like 0. Plus the Vy. So we have this right here. We can replace him right in here. I'll just put it there. Minus 1/2 g t squared. I said I wasn't going to work it all the way out, but I'm just telling you, if you could place this in here and here, and then you could set this equal to d sine 10, and now you have an equation where you can solve for d. Does that make sense? That approach?
Mm-hmm.
But I guess some of my point is that the projectile projectile motion problems aren't identical to each other. They got a similar thing going on right there, the same premise that because the times are linking the things together, that you're able to get it with geometry. This was like very similar to other problems that we had done, where we did almost identical actually to the tennis problem as an example, right? Where we're trying to find some, but once again, it's we have a coordinate that we wanted to meet with it, so we can find its initial velocity. It's a little easier here because it's completely horizontal. That makes it just a slightly easier problem. It doesn't have an initial y velocity. component. This is one that's actually been asked before. Kind of an interesting one where you're trying to lob something up through a window. I think, if I recall correctly, the wording of these can be kind of mixed up. The catapult is used to launch a ball such that it strikes the wall of the building at the maximum height of its trajectory. What happens at the maximum height of something's trajectory?
Velocity is 0.
The y velocity is 0, right?
Mhm.
So you can say, oh, but it gets to its very peak of the thing. So because of that, we'll be able to use this type of equation right here, set equal to 0, right? So that's sort of like the secret trick to it. But are we trying to find, launch angle. Launch angle can be hard. Can be a difficult problem. So determine the velocity VA at which it was launched, the angle of the release, and the height. It almost seems like it doesn't have enough information, but it does if you pick it apart and get the possible equations that can be used. Yeah, so this is a tough problem. Maybe I should work this problem out instead of just describe it. What do you think? Because it is unusual for a projectile motion problem. It's doable but unusual compared to some of the others. All right, so if it takes 1.6 seconds to travel from A to B, right there, that's one of the things that we have to work with. So delta t is 1.5 seconds. And determine the velocity. All right, so we have find VA, theta, and H. Not having H bothers me when looking at this problem, but they give us the time. We also know that the delta X is, that looks like 18 feet. Yeah, sure, 18 feet. They messed with us a little bit, where they're saying that YO, let's call it 3.5 feet. So, approaching any dynamics problem, we start thinking about what we already know, the things or the equations that we need to use. So here's one of the equations, and then right into there. So we can say, well, we know that we can treat XO as being 0. That was nice of them. So we could write out that we're going to have X is equal to V XO T. So we know that we're going to have 18 is equal to VA cosine of theta times 1.5. Two unknowns right there. Let's put a pin in it and keep going with the stuff we knew. We already kind of identified, because we were given the clue that the thing reached its maximum height. So we know we're going to have this equation right there. So, because I've already written it over there, I'll leave it out just to say that we're going to have 0 is equal to VA sine of theta and it's going to be minus 2 times 32.2 times, and that change in height is going to be h minus 3.5. We can work out some numbers right in here, but we do know here's another equation, and we have VA and theta are our two unknowns. It's still be sort of a hard problem to solve. I think we could do some manipulation here. We can probably, no, okay, well, we have 3 unknowns. The H is still unknown. Yep, so we still have 3 unknowns. So let's go one more. We have another equation that we don't have written down here. We have y is equal to, that's not true, sorry. Sorry. Vy is equal to Voy minus G times T. And that's probably the secret to this right here, is recognizing that's, we don't use that equation a whole lot, but it's valid, right? We're all on board that that's an equation that has to be true for the constant acceleration thing. So we say that we're going to have 0 is equal to the VA. Oh, by the way, this should have been squared. My bad. That should have been squared. I made a mistake, sorry. There you go. Now we're golden. Now we have this equation and that equation that we can solve. We have 2 equations and 2 unknowns. And probably they didn't bother doing it. Probably the way to go is to solve one of them for VA. So probably take VA is equal to 18 divided by the cosine of, we need to divide by 1.5 to the cosine of theta and 1.5. All right. And then plug them into here over this one. So we're going to get, what? 18 over 1.5, and then sine of theta divided by cosine of theta is equal to 32.2 and 1.5. So we can see that we're going to be able to get the theta because we can take that turns into tangent. And the answer according to this is 76 degrees. So let's see if we get 76 degrees. So we go 32.2 times 1.5, boom. Multiplied by 1.5, divided by 18. Hopefully that's, ooh, that's not good. No, I think we're okay. A tangent, we could take a tangent of a number that's larger. So, I almost took the inverse tangent. Calculator still in radians. Don't fall for that, man. I mean, I wouldn't take but like half a point off or something like that. Don't. I mean, maybe I don't know, maybe a point. It says 76.04. 76.04. Oh. And now with that, you can find out what the initial velocity is. And now that we have that angle and that initial velocity, we can find out what that h is. So you see the method, right? But it's not identical to one you've done before. I get sometimes, but I think I don't get anything anymore because I stopped it before you can write it down on the course evaluation. The exams were nothing like the home. They were. They just weren't the same question, right? It's the same skill set that I'm trying to measure, right? If we don't do this, you can't progress. Become the kind of engineers that you want to, and the jobs that you want to get, that kind of thing. I think I oversaid this, but I'll. But anyway, okay, so let's talk about other problems. There's several other combinations. This is one that I would never ask you for, is this angle. There's a hard problem. I could give it away. The trick is you do a quadratic. You have to get, you take the, well, no, actually, I think it might have one of these. there's like an identity. To one of these, it has like an identity that you wouldn't know, like a trigonomic identity. It's like a secant. Like the secant squared is equal to like 1 minus the tangent, or 1 plus a tangent. So anybody remember that? Why would you? I don't know. Because you have Wolfram alpha, right? Why did I take all these classes? I could just have a computer do it for me. Anyway, I just wouldn't do that to them. It's one of those problems. All right, so ask me questions. I'm here for you. We got 35 minutes left.
You don't have to do it, but if you can just explain the process for homework 4, problem 2.
Okay, sure. Oh, absolutely. I was just grading it. So, yeah. Absolutely. You can ask those kinds of things anytime about it. I'm done with it. Let's see what's going here. Is anybody joining us remotely, by the way? I have yet to see anybody. Okay. I meant to record it there too because I don't know how I can take roll. Dr. Orlip said, I told people they could get credit for showing up remotely as well. And I'm like, I did not think about it. Homework solutions. Homework assignments. Let's look at the assignment. So, boom. Chrome or Adobe really wants me. Okay, so I got the runners on the track team. So, the runner A, thank you. Runner A is going at 4.5 meters per second in a straight section, and his speed is increasing at a rate of 0.5 meters per second squared. Runner B is going around that curve right there, with this has a radius of 45 meters. Moving at 5.5 meters per second and decreasing speed at 0.75 meters per second squared. At the instant shown, runner A is that distance away. And I'm pretty sure that distance doesn't matter. That's my recollection. That's just one of those tricky ones. Like it doesn't really matter. So mostly what this is a coordinate transformation problem. Because we have the velocity of A, we're told, is 4.5 I meters per second. And the acceleration of A, he's increasing speed, right? So he's going to have a 0.5 I. Whereas B is going to be moving at 5.25 meters per second, but we have to try to figure out which way that we're going right here, right? So we would probably want to find this with respect to horizontal. So when looking at this, I almost have to draw like a little diagram right out here. He is coming in a path right there, right? So he is right here, so he's going to be going down that way right here, but he's got this angle right here, so that's the angle right there. That right there and that right there have to be the same angle. Am I correct in that? Yeah, because if you close this angle down, that angle closes too. That's my way of trying to, anytime there's a tricky thing, to try to figure out if the angles are the same onto the thing, is to try to shut the angles down and see if they both close. And that would be true right there. So therefore, this one, which we would typically use, is actually going to be 60 degrees, right? So we want to break this thing into 5.25 times the cosine of 60 degrees I plus negative 5.25 sine of 60 degrees. All right, so we get the values. And then we also, let's see, and I'm asking for the velocity of B relative to A. And I never did say what coordinate system that should be in, but I probably should have told you what coordinate system I wanted the answer to be in. But you could, probably the best way to approach it is to just give a magnitude and an angle and a quadrant. So I should have made that clear that that's what I wanted. And I'm not sure why I didn't do it. It seems like I recognized this previously and wanted to. But anyway, so that's for the velocities, right? For the velocity of the thing. For the acceleration, we have a little bit of more work to do right here. So we have the acceleration of B, and we know tangentially that he's decreasing this way, right? So he's going to be a negative 0.75. ET. What we're also going to have is centrifugal acceleration, which is going to be pointing in the normal direction. And that's going to be v squared, so it's going to be his 5.25 squared and divided by the radius, which is 45. En. So, the main thing that we want to try to do is get the velocity of B with respect to A. That's what we're being asked. So that's the velocity of B minus velocity of A. And then we also want to have the acceleration of B with respect to A. But in order to do this, especially the acceleration, I mean, we're actually pretty much set. I didn't actually have to do the coordinate transformation for the velocity because I just thought my way through this piece right here. But the acceleration is more difficult to do. So here, using the coordinate transformation is the way to go. So you get the acceleration of B minus the acceleration of A. We need to get them into the same terms. It's easiest to, because we already have this in rectangular coordinates, let's turn this into rectangular coordinates. So we set up our coordinate transformation. And we say that here is I and J. And for this setup here, let's see, we're going to go, right there is our tangential. And our normal is going to be like that right there. And so, and in terms of our angle, because they define theta, I'm going to go ahead and use theta for everything. There's theta is right there, right? Right there is the normal direction right there. So there's a tangential direction. So I think I got theta correct. Theta is right there, theta there, theta there. So I have my I, J, go E, T, and E, N. And so you could go in either way, either the I's, going from here to there, from there to there. This one's like a little bit, challenging. No, I think we're okay here. I think I didn't do a great job of writing this thing out, man. I'd like to make it. It looks to me like the I, when comparing it to this right here, is going to be the sine of theta, and it's going to be positive. I'll double check on that, but I think I did that right. And one of the ways we can check on it is we can do the other ones too. And if I come back to this, I go, oh, that sign doesn't make sense. It doesn't follow the pattern that we're looking for in the coordinate transformation, I might think back of that, but I'm looking at I and the tangential. They seem to be in the same direction right there. Yeah, okay. And then I'm going to go I with the normal, and then that looks like it's going to be negative cosine to me, right? Because it's I right there. They're in the opposite direction, and it's the adjacent right here, so that's going to be negative cosine. Then I take a look at the J and compare it to the tangent within the opposite directions from each other, the J and the tangential, and it looks like cosine, so it looks like negative cosine to me. And then lastly, I'm going to go the J with the normal. And yeah, so that's going in the negative J, and it's going to be the sine. It's going to be a negative sign, so that should be right. Is that okay? Yes, sir.
Wouldn't it be 30 degrees instead of 60 degrees?
For this one right here, I forgot. my mind was wandering, and I totally forgot about the coordinate transformation. So I was just thinking my way through what would be. I know, but this would be the sine of 30 degrees, and this would be the cosine of 30 degrees. So you get the same thing. I'm pretty sure. I think I did it right. I don't know. I think I did it right. But I was just looking out to think that it would be the complementary angle when it comes to trying to find break the thing into the x and the y. He's definitely going down more than he yeah. So that sine comes out to like the 0.86 whatever thing. I think so. But it's probably better, instead of doing this, you actually use this coordinate transformation matrix. And so, no, I don't know. I think it's fine. He's in the tangential direction. So what we should do is go, sine, it'd be sine of 30 and then negative cosine of 30. Yeah, so it would work out. Yes, it would work out. So now for here, with this value right here, we would work through this. Do you need to see that, or we could do?
That's good.
Okay.
I was confused upon to that part. So
Okay.
that helps. Thank you.
This right here takes practice, by the way. I mean, it once you do it like 3 or 4 times, you'll feel much more comfortable in doing it. But seeing someone do it can be like, okay, yeah, I see what you did there. But actually doing it yourself is very necessary to really build those skills. Let's see, we haven't done a dependent motion pulley problem yet. There's not many in here. There's that one, and if I'm not mistaken, this is a this is not an FE. I don't have many dependent motion problems in here. Jeez. I need to put more dependent motion problems in. So maybe I should write one. Or we should pick one out of this thing that I have up here called, under notes, notes and videos. Let's see where the pulley problems come to. Oh, pulley problems were right there. Suggested problems in addition to homework. What do you think? Should we do this one? Do you think I can? I don't know if I can. Maybe I can. I think I actually printed out this solution because I was like, oh boy, I don't know if I can do that problem. I haven't done it before. Pulley problems are mainly about setting them up correctly. And then, not so bad. And then the rest is usually just some algebra. We really only had one of them on the homework, I think, so it's gonna be. maybe that's something we should emphasize too much, I don't know. He said an athlete pulls handle A to the left with a constant velocity of 0.5 meters per second. Determine the velocity of weight B and the relative velocity of B with respect to handle A. All right, so I don't know of any other way to do this except to try to sketch the thing out. There's a bunch of stuff in here. I think I'm starting to suspect there's a couple things that are completely unnecessary. Yeah. All right, let's just not worry about it too much. There you go. Something like that. And these guys right here. Okay, so there's a lot of things here where the lengths aren't ever going to change. I think I missed finishing this up. I had finished it and then I punted. Like, for instance, this length right here never changes. This length right here never changes. This length never changes, and this length never changes. So we can just ignore all of those. Right here, we'll set up this to be, I'm going to call it SA, right? So because this length can change. And I'm going to call this SB. Because this length, that length, that length, and that length can change, right? And I think that's it. This one definitely can't change, that one definitely can't change. So if we're looking at for the length of this, total length of this thing, you go SA plus 4 SB. VA plus 4 VB. And we're not asked anything about acceleration, so we don't need to do that in this problem. And so they say add, so to the left. So I guess we could just go ahead and say that VB is going to be negative 1/4 VA. But remember that anytime when it comes to the positive and the negative, they all depend on what you used as the coordinate system right here, right? So that means it's going, obviously, if this is positive and this one's negative, that means it's going up, right? Which you usually think of as positive, but it's just the negative there is all about what we call that. Yes, it is getting shorter. Yes, the velocity is going in the negative coordinate of SB, which happens to be up. So I a lot of times just like to go the absolute value, and then you know what you just say you know what the direction is, right? Kind of. If it's complicated and you're not quite sure what direction something's going to go ahead and use, but carefully use the directions, but make sure that they're consistent. So you're going to go, this ends up being 0.25 times 0.5 or 0.125 meters per second. And so we find the velocity of B. We're going to answer it. We would say 0.125 meters per second. And remember, if they say the word velocity, velocity is a vector and requires direction. And the hat requires a hat. When you say acceleration, they almost always mean a vector. But if they say the acceleration magnitude, it's just a value. And here we want the relative velocity of the weight with respect, so we had to go VB with respect to A, VB minus VA. So we get 0.125 J minus, but then minus 0.5 I. So you can obviously see that B with respect to A is going to be 0.5 I plus 0.125 J but quite often that doesn't tell me nearly as much as to say find the magnitude and the angle. So 0.5 squared, 0.125, and you get 0.5154. Find the angle, B with respect to A, inverse tangent, 0.125, 0.5. And they didn't bother giving me, they only gave me 2 sig figs, a bunch of liars right there. Comes out to like 14 degrees. Maybe it comes out to exactly 14 degrees. They left it up, I don't know. 0.125. 14.04 degrees. So if you're going to give an answer, V, B with respect to A, 0.5154 meters per second, and that's in the first quadrant of 14.0 degrees. I'll give it another sig fig. Why not? That one wasn't all that hard, right? But it looked hard. It looked intimidating, right? When you first looked, didn't I don't know. Maybe it's just me. When you first looked at that, you're like, damn. But just picking it apart, taking your way through it. One of the most frustrating parts about dynamics is almost all the problems look easy once you see the answer. Once you see it's done, you go, ah, that made sense. It's going the other direction, looking at the problem and attacking it and recognizing what's happening underneath the hood. Got 10 minutes? Want to do something else? Other kind of problem? so quiet. How can I make you feel more at ease? Am I intimidated? I don't think I am. Oh no. You know what would really help? Is if my wife would come to class. Everybody loves Lori. Everybody's always asking, what the hell are you doing with her? How did you do that? I'm like, thanks. But everybody, that's why she's a good pharmaceutical sales rep. She goes sees doctors. Doctors love her. Nurses love her. The receptionists love her at that doctor's office. She's just nice. She's a nice person. She thinks I'm okay, so that means I'm okay, guy. So if she can vouch for me, I can't be intimidating. If Lori Dapper married the messy-haired kid that sat next to her in high school, I must be okay. Did I tell you the story? Alphabetical order. Mrs. Wright, our senior year in AP English, didn't want to bother learning our names. I don't know. Made us sit in alphabetical order. I sat next to my best buddy, John Doty, who's the valedictorian over my right hand side, with this blonde girl named Lori Dapper on my left. And everybody expected me to try to cheat off of him. So I cheat off her. It's a bad kid. I went to a military academy, got some honor out of that. So I don't cheat, but back then, yeah. I used to write on her notebooks, like, you know, I was one of those kids, right? That just take the girl's notebook that's next to you. They sat me next to a pretty girl. I didn't know how to behave, so I write on her notebooks, on the cover of her notebook, I'd make like skulls and things. Saw the world exploding, bad things. And her mother was like, Southern accent. I'll do an impression. Lori, who's writing on your notebooks? It's just this stupid kid that sits next to me. So I don't know if my mother-in-law knew it, even to this day, that it was me. We've been married 30 years, so I don't know if she knew. I was that stupid kid. I think she did. Surely that's right. Don't be intimidated, Brendan. Ask me questions and stuff. We can still do more questions. I'll hang out. No? All right. Hope this was something useful. Send me emails with questions about stuff. I'll post the solutions. Actually, I don't know when I should post the solutions to the practice problems. I want you to work through them, though. I really want you to work through them. Oh, thank you.
Thank you.
Thank you. Have a great weekend.
You too.
Don't spend all your time on dynamics, but some.
I forgot the time.
Oh, please. I can find one somewhere. Sorry, I didn't have this. I should stop recording. I don't know if this was the greatest recording. Let's see.
As long as you can hear yourself talk.